Halliday and Resnick, Chapter 4, Problem 91. During volcanic eruptions, chunks of solid rock can be blasted out of the volcano. These projectiles are called volcanic bombs. Figure 451 shows a cross-section of Mount Fuji in Japan. A. At what initial speed would a bomb have to be ejected at angle of theta 35 to the horizon from the vent of A in order to fall at the foot of the volcano at B? At vertical distance, height 3.30 kilometers, and horizontal distance D 9.40 kilometers. Ignore for the moment the effects of air on the bomb travel. What would be the time of flight? Would the effect of air increase or decrease? Your answer in A. So we're going to set 0 at the bottom or the base of the mountain. And we're going to use this formula for constant acceleration. Y equals y sub o plus v sub o sine theta times t minus 1/2 g t squared. And we're just going to plug in some known values now. So we know that y at the base of the mountain here is 0. This equal y sub o, which is this point here, and that is 3.30 times 10 to the third meters plus v sub o, which we're looking for, sine theta times t minus 1/2 g t squared. Now we're going to make a substitution for t, and we're going to get it from the fact that the cosine, the velocity for the cosine, moves at a constant rate. So v cosine is going to be v sub o cosine theta. And that will go to, since we know what d is, that'll be d. It's going to equal v sub o cosine theta times t. And we'll solve for t. So t is going to equal d divided by v sub o cosine theta. Now we'll plug this into our formula here, which we have. We'll just take this on the other side. We have minus 3.30 times 10 to the third meter is going to equal v sub o sine theta times t, which is going to be d over v sub o cosine of theta. D we know is 9.4 kilometers. So let's put that in, 9.4 times 10 to the third, that's in meters, and it's going to be divided by V sub O cosine theta minus 1/2 9.8, and it's going to be this t squared. Well, t squared is going to be 9.4 times 10 to the third divided by V sub O cosine theta, and all that's going to be squared. So we come with minus 3.30 times 10 to the third meter equal sine over cosine is tangent, and these cancel. 10 of 35 degrees times d, which is 9.4 times 10 to the third meters, minus 1/2 times 9.8 times 9.4 times 10 to the third meters, and that's squared over V sub O and cosine of 35 degrees. So I'm going to do all this math and get right back with you in a second. All right, when we do the math on this, we're going to have 3.30 times 10 to the third. Now that's just the height of the mountain, which equals 6.582 times 10 to the third meter. That's this portion right here, 1035 times 9.4 times 10 to the third, minus this section here, which is 1/2 times gravity times this expression d, which over V sub O cosine theta squared. That's this expression here. So now we will take this on the other side. We have 6 point, that's a minus, 582 times 10 to the third minus 3.30 times 10 to the third equals minus 6.45 times 10 to the 8 divided by V squared. We got that V sub O squared. And this goes to V squared, V sub O squared, which would be V sub O squared is going to equal this will go up here, and this sum would come down here. The minuses make everything plus. So we have 9.882 times 10 to the third, and this will be 6.45 times 10 to the 8. So V sub O is going to equal the square root of 6.45 times 10 to the 5th divided by 9.822, and that will equal, that'll equal 255.4 meters per second. So that's V sub O. That's part. So now B wants to know the time, and we're going to use this formula we developed earlier. T equals D over V sub O cosine of theta. So T is equal to the distance D, which is 9.4 times 10 to the 3rd meters. V sub O, which we have as 255.4 meters per second. And that's time the cosine of theta, which is the cosine of 35 degrees. So T is going to equal 44.9 seconds. C, would the effect of the air increase or decrease your answer? What we call the effect air resistance. So if it's going to resist it, it's not going to be helping. So it will decrease.